Yikes. Can everyone see my screen? Okay, cool. So let's get started. All right, so welcome to Lab 3, everyone. Happy Monday. Today in Lab, we'll be going over some more complexity analysis, amortization, especially dealing with vectors, and also some string stuff. So a few quick announcements before we actually get started with today's content. Project 1 is due tomorrow, so hope you guys have at least started, and hopefully you guys are close to being done. You can use 1 late day to submit on Wednesday, and you can use 2 late days to submit on Thursday. And then Project 2 will be released shortly, and it'll be due on October 13th. Your Lab 2 quiz and autograder are due on the 25th, and then your Lab 3 autograder and quiz will be due on the 2nd of October. And then your midterm is October 21st. There are no labs during the week of the midterm, and there will be a review lecture. And there will be more announcements to come, and also some stuff on how to actually sign up. We'll be making a Piazza post about that shortly, so don't stress too much about the exam right now. And so looking more into what we're actually going to be doing today, we'll be taking a look at recurrence relations, and specifically how we can find the runtime of these using the master's theorem and also the substitution method. And then we'll be looking at how vectors are actually implemented under the hood and vector amortization. And then we'll take a quick look at the difference between C-style strings and also C++ strings. And then at the end, we'll have some time to do the handwritten problem together if you guys do want to talk about that. So let's jump into recurrence relations. So a recurrence relation is basically an equation that is defined in terms of itself. It usually also defines a sequence of values. So think about the Fibonacci sequence. And so many algorithms will have time complexities that are modeled by recurrence relations. Later on, we'll learn about dynamic programming, and dynamic programming is almost always modeled by a recurrence relation. And so if you want to see here, we have this f of n. F of n is defined in terms of f of n minus 1 and f of n minus 2, and that is why it is a recurrence relation. And so we can use this thing called the master's theorem to actually find the complexity of certain recurrence relations. But it is important to note that in order to use master's theorem, it has to be in this form. And also these have to match. And then if you're able to rewrite your equation in this form, or your equation just written in this form, you're able to just pretty much plug and chug right here. So, oops, sorry. Okay, so we'll go through this example. Given the master's theorem, what is the complexity of the recurrence relation? So if we look at this, we have A is 8. Let's look at the current slide, last slide, sorry. And then we need B, B is 2. And then C is actually the kind of like the exponent on this last term right here. So this is technically n to the 1, so C is actually 1, right? And then if we look at this, 8, and then B to the C is 2 to the 1. So this A is greater than that. We have it in this form right here. And so once again, we have it in this form right here. If we once again just plug and chug, we get n cubed. And if anyone has any questions throughout this lab, just feel free to unmute yourself or type it in the chat. It is kind of hard to like check the chat. So like I would prefer you to unmute yourself, but like, yeah, I will be checking the chat once in a while. So in the case that the equation you're giving is not in the form where you can use a master's theorem, we can also use the substitution method to solve it. Sorry, let me, yeah. So we can also use the substitution theorem to solve it. So in this case, we can't use a master's theorem here because this term has an n minus 1. If you remember from the previous slide, in order to use a master's theorem, your term here kind of has to be like n over b. So we can't use that. But we do know the base case. It is given here, this t of 1 is equal to 1. And so pretty much we can keep substituting. You can keep substituting like the equation back into itself until you find a pattern, and then you can reach a base case. We'll actually take a closer look at this. We'll go through an example. I feel like it'll make more sense when we actually look at it. So here are the actual steps. So first you want to substitute the formula into the recurrence terms on the right-hand side of the equation until a general pattern is found. And then you pretty much want to solve for k such that the base case is present on the right-hand side. So once again, we'll take a look at an example, so please don't feel like totally lost right now. All right, so step one is, once again, we're substituting the formula for t of n into the recurrence terms on the right-hand side of the equation. So this is our original equation right here. And basically the subproblem, we just see t of n minus 1. And then you want to kind of substitute it here. So t of n is equal to 2. And then we want to substitute this t of n minus 1 in the subproblem into this t of n minus 1 here. So we'll do 2 times t of n minus 2 and plus 1. And don't forget about that 1 up here. And then this subproblem right here, we'll just decrease it by 1 term. So t of n minus 2 is equal to 2 times t of, I think it's like n minus 3 plus 1. Yep, so pretty much what we wrote on the previous slide. So once again, we're just substituting the subproblem into this part right here that's circled in red. And then they also simplified it a little bit. So this is just the simplification of it. And so pretty much we're going to keep going through this process. We'll do it for 4 terms, which is usually kind of like a good number to do. And once again, we just see the subproblem over here. You just decrease it by 1 every single time. We're just plugging and chugging. And so we're at our 4th term now. And usually this is a good time to actually look and see if there is some sort of general pattern that you can generalize for the kth term. So if we look here at this bottom portion right here, we will see that there's 1, 2, 3, 4 2's in the front. And then there's this t of n minus 4 term, right? So we can kind of generalize this to be 2 to the k multiplied by t of n minus k. And this right here, this 2 times 2 times 2 plus 2 times 2 plus 2 plus 1. You don't need to know this, but this is actually a summation. So this is actually k is equal, or I is equal to 0, k minus 1, and this is 2 to I. That's actually what that is. Yep. And so once we have this generalized equation in the terms of k, you pretty much want to solve it for, this slide is super messy. Anyway, we pretty much want to solve it for this, where we want to solve for t of n minus k, since we can basically plug in our base case on the right. And so t of n minus k is equal to, like, we pretty much want to solve for this right here. And so that's equal when k is equal to n minus 1, if you just rearrange like the n minus k equals 1. And then pretty much what we want to do is we want to substitute n minus 1 for any place we see k in this original equation up here. And so if we actually do that, we'll get 2 to the n minus 1 times t of 1, since we already know that that's n minus k in this case will be 1. And then plus some summation. I'm not going to write out the summation because it's kind of pointless, but 2 to the n minus 1. We know t of 1 is equal to, I believe it was 1. And then we get this. If you look over here, they actually give you this because you don't need to memorize the summation rules once again. It'll be plus 2 to the n minus 1 minus 1. So that's how they get this right here. Let me check the chat to see if there are any questions. Okay, perfect. Okay, so we're actually going to do some practice now, identifying recurrence relations. Does anyone have any idea on what the answers could be for this? Okay, I'll just run through it then. So given the function below, calculate the recurrence relation. So we can assume that bar n runs in log n times. So let's just look at this. So this is log of, oops. This is log of n. All right, so let's take a look at this. So we have this function foo. So this, if n is equal to 1, that's some like constant time stuff, doesn't really do much. This is a call to itself, so we'll do t of n minus over 4, sorry. So we have this some more constant time stuff. And then we have this for loop. For int I is equal to 0, I is less than k, so this is n squared, as seen in the previous step. And then we have a nested for loop from j is equal to 0 to j is less than n. So these two nested for loops will run n cubed times, right? Since we have this n squared and this n right here. And then so we know that bar n is log n of time. So this entire statement right here is n cubed log n. And then we have, oops, my mouse is disappearing. We have this final for loop for int I is equal to 0 to n. We have this foo of n over 2. So this is once again a call to itself. This will be expressed in terms like this. And since this runs n times, we'll do times n. And then so if we put that all together, we get t of n over 4. And since these aren't nested together, we'll just be adding them together. And then we'll do n cubed log n. And then that final statement right there, n t of n over 2. And then, oh, actually, I forgot about this bar k right here. This will run in log of k times. Plus log of k. Let's see if we're right. So let's walk through the solution. So once again, foo is a call to itself, so you'll express it in terms of like t. So that is t of n over 4. Then we have the for loop that runs n of log n, but it is nested in another for loop, so you'll multiply it by n squared. So that will give you n cubed in the end. And then we finally have this other for loop that will run n times, and it'll call itself. And then we have this bar k at the end. So I'm just going to, so I'll walk through the solution. Oops, I must have not erased the slide. Give me 1 second. What? Oops. Great, now it is not erasing. Give me 1 second, guys. Sorry, I must have not erased this when I was looking over it the first time. Okay, I think we're good. Sorry about that. Oh, that is not the right side. Okay, so this was the function we're looking at. I'm just going to go ahead and kind of go through the answer. So in the yellow stuff, we have some constant time stuff. Is this? Okay, yeah, we'll do this one. So in the yellow, all the yellow stuff, we just have some like stuff that runs in O of 1 time. So yellow, this is just stuff that runs O of time. So like declaring variables and kind of like if statements. And then we have this while loop. So while x is greater than 4, but, and within this while loop, we are calling foo of n minus 4. So this is where, oh, I'm sorry, not n minus 4, n divided by 4. So this is where this term comes from. And since there is some other constant time stuff associated in this while loop, this is where this +1 comes from. And since this is running 4 times, and we are dividing by 2 every single time, this is where you get this log of n minus 4 term. And then, so we'll look at this red for loop right here. So this runs from I to x, where x is n minus 4. And then, so every single time this for loop is called, we also will be calling foo of I. Foo of I is actually just a constant. So we'll just, that's where the 1 comes from. And this will pretty much run 4 times because we already know that by the time x is done with this green loop right here, it'll be at most 4. So that's why we have this actual 4 here, because in the end, this loop will actually only run at most 4 times. And then the blue and the purple just come from these 2 calls right here to foo. All right, so now let's actually jump into some discussion about FTL vectors and how they're pretty much implemented under the hood. So to start off, vectors, they all have a data pointer, a size, and a capacity tracker. And so the capacity is how much room the vector actually has, whereas the size is how many elements they actually contain. So for example, if we have a vector here, so this vector has a capacity of 4. But let's say there's like a 2 in here, right? The size is 2. I mean, the size is 1, sorry. And then, so it's important to note that there is a difference between calling vector resize and reserve. So when you call vector resize, it'll actually change the size and increase the capacity if needed, but it'll actually initialize these elements. So if you call pushback again, it'll add a new element after the ones you already created. So let's take a look at this. We'll say we call vector resize, and we'll say we said 4. So I think the default initialization for an integer vector is 0. So what your resize will do is it'll create these 4 spots, and it'll actually initialize the element in every single one of these spots with a default value, right? So if you call push back again, it'll actually push back a new element here. So I'll have to create like new capacity. So if you use resize, you'll pretty much just want to index in afterwards. So if you want to change something, instead of calling pushback, you'll want to use this. And then with reserve, it only changes the capacity. So calling pushback will actually add the x in the same place as before. So let's do vector dot reserve. Let's do 4 again, right? So 4. So we have a capacity of 4 here, and if we do vector dot pushback, we'll do a 1. If we do vector dot push 1, it'll actually add it here. Whereas if we did a pushback in the resize one, so if we did a pushback here, 1, it'll actually add a new like capacity element as well. And so kind of before, when we introduced the vector, we told you not to worry about its implementation, but we told you to use resize and reserve, because if you don't do it, capacity increases are expensive is pretty much what we said. And so we kind of want to go backtrack to what we were saying earlier and kind of tell you why it's important to use resize and reserve. Pretty much if you don't tell the vector what size it should be, the capacity of your vector may be way, way more than what you need, and that's a lot of memory wasted. So let's take a look at, so this is pretty much just kind of going back to what I was saying. So we have this data pointer. This is actually the size. I think this is, yeah, capacity. So we have this data pointer pointing to the actual vector in memory. we want to push back a 6, right? And so there is extra capacity in our vector, so we're able to push it back in O of 1 time. And our size is increased, as you can see in the green circle. And then say we want to push back another number, this 5. Our vector is currently at full capacity right now. So what will happen is your vector will go ahead and actually create a new vector of double the capacity. So this new vector is of capacity 8, as you can see in the green circle. And what will happen is you'll copy over all the old elements. So 1, 2, 3, 6. And then you're finally able to push back this 5. But this is important to note, because what if we want to store 4,100 elements in a vector and you don't use resize, but you only call pushback? So as we saw in the previous diagram, your vector capacity will actually double. So it'll go from 1 to 2 to 4 to so on. And then once you insert the 4,097th element, the vector's capacity will actually double to something in the 8,000. So if you're only storing 4,100 elements, then there's like half the vector is just wasted. Okay, so let's now move on to amortization. So amortization is pretty much just another way to measure the cost of an operation. We've already learned about worst case. This is usually like our big O of N stuff. And then we also have this thing called average case. So what is the expected value of resources needed? And this is kind of like, think sorting. I think there is a chat question. I know this is very project specific, but for a case like the complex dictionary, the project has something like that, haven't we reserved double the memory we need? Okay, I'm not entirely certain what the project implementation is, but I think, isn't there like, don't you read in the size of the dictionary before you actually start reading in like the words? If that is the case, then you should be able to do vector.reserve. But if not, then like if you don't know the size of your vector before you actually run through everything, then in that case, like there is no way you could call reserve or resize. And yeah, okay, thank you, Nick. So you can do reserve for the simple dictionary. So once again, the worst case is something we kind of look at frequently. So this is usually our big O notation. And then the average case is kind of like, what is the expected value of resources needed? So if you think like sorting algorithms, right? I think a lot of the sorting algorithms, like the basic ones, there's a lot of ones that are like O of N squared. Let me check the chart really quickly. Reading the number of entries. Yeah, once again, I'm not too certain about the implementation of the project. I mean, if you don't know the size of the dictionary beforehand, then there is no way to call reserve and resize. So, I mean, the project, like the autograder won't flag you for that because that's like the only way to do it. So with regards to sorting algorithms, a lot of sorting algorithms are O of N squared time, but this is the worst case. So it's pretty much like if you were trying to sort like A, B, C, D, it's very unlikely that your input will be the exact opposite. So like B, C, B, A. Like if you're trying to sort something alphabetically, it'll be very unlikely that every single letter will be, you know, in the exact wrong place. And so now we move on to this concept of amortized analysis. It's different from average analysis because amortized cost is a collection of operations, whereas in this worst case and average case, it is the cost of just an operation. And we use this amortized complexity to describe the runtimes of things when the worst case is too pessimistic. And so we'll take a look at this later with vectors in specific. But I think this is a bit helpful. This is kind of just to clear any confusion on what the difference between them are. So let's say we're talking about paying rent, right? So you pay $600 of rent on the first day of each month, and there are 30 days in the month, right? So it is true that $600 is paid on the first day of the month. But for the remaining 29 days, you also don't pay anything. So it is really pessimistic to say that the daily cost of living in an apartment is $600 just because you paid, $600 for that one operation. So with amortized complexity, you can think of it like with the $600 payment, you can live in an apartment for around 29 days without paying, and it actually comes out to about $20 per day. Let me check the chat really quick. Also, to clarify on the project things, another student just clarified, there probably is nothing you can do to reserve or resize on the complex dictionary. And so back to amortized complexity. Amortized complexity does give you a better approximation of the complexity when an operation, if the worst case is too pessimistic. So let's think back about vectors, right? So the worst case time complexity of actually pushing an element into a vector is, oops, I need to be able to write on this, is O of n, right? Since if the capacity of the vector is all filled up, you will have to reallocate a new vector and copy over all those elements and then push back the new element you're trying to insert. So that is O of n. However, most of the time when you are pushing into your vector, you don't need to do this copying process. And it's just an O of 1 operation where you just push it into the last, where you just push it into the vector. So it would be a bit extreme to always say that pushback is an O of n process. And so let's kind of look at this in more detail. So let's fill up a vector calling pushback over and over. This gray part is the filled space, and then this white part is the unused capacity. And when we run out of capacity, we'll be doubling it, right? So we're starting off with this vector of capacity 1, and then we're filling it, right? And then we want to push in another element. So what will happen is that, this will get reallocated, all the elements will be copied over, and then you're able to push the last element in. And then we want to push in another element. So once again, your capacity is full here. So what will happen is you will go grab another vector of double capacity, so size 4, and then you're able to push in your new element. So if we keep going through this, this is kind of what it will look like. And that should make sense. And then so we're marking all the ones that got inserted as red. So every single time we're pushing back one element. And then the ones that got copied as blue. So every single time the vector runs out of space and you want to push in another element, that's when you have to copy everything over. So those are the times where your vector runs out of space and you need to copy everything over. And so if we look at this diagram, we can actually tell how much time a pushback took at each of these. Pretty much the time a pushback took is the number of blue plus the number of red. Because the blue are things that you have to copy over, which will also take time. And then the red is the thing you're actually inserting, which will also take time. So right here, this would be 3. Right here, this would be, hold up, I actually can't actually see that. 1, 2, 3, 4, 5, 6, 7, 8, 9. This will be 9. And then I believe the last one over there is just 1, since there's only a singular red element. Yep. And then so, oops, sorry, let me take care of this really quickly. So the time a pushback took is equal to the number of red blocks plus the blue blocks. So let's get rid of everything else so we can better visually kind of see this. And so now the height of each tower is the cost of each pushback. So as you can see, most of the towers are just one red element that represents our O of 1 pushback where we don't have to reallocate anything. But each of those blue towers does represent when your array or vector is full and you want to push another element in, you're going to have to copy over all your old elements first before you're actually able to insert that new one. And so now we're going to kind of amortize the cost. So basically, we're going to spread the blue box around to see what happens, kind of similarly to the rent situation, right? So the rent situation, we wanted to divide it by every single day of the month. And so now if we look at this, like every single basically push we do is like, it will take 3 things. So technically it is constant since it takes like, it's like O of 3. And so once again, like the total is the same, but if we do kind of divide the amount of work we had to do among every single operation, it kind of does spread out. And that is kind of the idea of amortized complexity. So pretty much this is an O of 1 process. So to kind of finish off this topic, when a vector reaches capacity, it reallocates and the capacity doubles. So the capacity jumps from n to 2n. And so even though this is an O of n operation, we do get n free pushes of O of 1 time after this operation. And if you want to look at this kind of from a more mathematical sense, we have this O of n operation that is the reallocation. We get n free pushes, and this kind of averages out to O of 1 time. And this is actually a really cool concept. What if the vector only reallocated with a capacity of n plus 100 instead of doubling? If you think about this, it'll be, so this, if you think about this, right? The reallocation process will still be O of n, right? Since you still have to copy all those elements over, but the number of free pushes you get is no longer n, it is actually 100. And if you think about this, this is still O of n. And so that's why it's super important to kind of know that the vector capacity actually doubles, because if it were to increase just with a constant factor, then pretty much it will not be amortized O of 1. And a final comment about strings, vectors, and other auto resizing containers that may go reallocate the memory when they're full and move their data. When this happens, when you have to reallocate to a bigger vector, any pointers to your old data will be invalidated. So let's say we have this, let's just take this vector 10 example. So let's just say there's like 10 elements here. That's probably not right. And then we need to, so say these are all full and we want to resize, right? What will happen is this chunk of memory will get pretty much deallocated and the compiler will be like, oh, you can go use this for something else. And this will be your new vector. But if you had any, okay. But if you had any pointers pointing to this old vector and you reallocate a new vector, then this old pointer will basically be pointing to garbage. And that's what we mean by pointer invalidation. And this is something that you want to remember for project 2, actually. However, if you do call vector resize or reserve beforehand, your vector will never be your vector will never be reallocated if you do use it correctly. So if you call resize or reserve, you don't have to worry about pointer invalidation. And once again, very important for project 2. And so a kind of a final summary on amortization, just to really hammer this idea in the head. Basically, you're measuring the total cost of a sequence of operations rather than one. And even though some of your operations may be expensive, such as the vector reallocation that is O of n time, the majority of your operations will be cheap, such as the rest of the pushbacks that you are able to achieve in O of 1 time. So looking at the most expensive operation is kind of too high and too pessimistic, and that's why we use this amortized complexity, this idea of averaging out the expensive operation over the cheap operations to get a more realistic idea of how our code is actually going to run. And we're going to just do a quick lesson on C strings and also C++ STL strings. So C strings are basically arrays of characters terminated by a null character. These are different ways you can actually declare it. But it is important to note that the last thing in each C style array will be this sentinel character that tells the compiler that, oh, my string is over. And it's important to note, right, since even though Bing only has 4 letters, we do need to create an array of 5 for the sentinel character. And you also do have to add it here. And then we also have C++ strings. I'm sure you guys are pretty familiar with these by now. Basically, C++ strings, you can declare them like this. And also it has many member functions. I'm sure you guys are pretty familiar with size and length, and also this bracket operator. And you can do pretty much, this is a comparison between finding the string length of both a C-style string and also an STL C++ string. So with the C-style string, you actually have to call a function and then pass a string in as an argument. Whereas if you have a C++ string and you want to find the length, you just use the dot operator. And basically, final note on this is pretty much you want to use C++ strings over C strings. I don't think I ever used a C string in 281, and you probably shouldn't either. You know, a couple notes about this is the size is stored on a C++ string, so you don't have to keep track of that sentinel character. There's just more functions that are supported with the C++ STL string. And also some C++ STL string functions are actually faster than their C string counterparts. So I'm going to stop the recording here. How do I do this?